All right. Any questions before we get going? Go ahead. Well, yeah, it's a long section. Hopefully this is the last of it. I think it will be. I'm guessing by the fact. Yeah, I didn't quite get as far as I wanted to on this thing last time, but let's keep going. So we'll talk about log functions, inverse functions. So if a is a number bigger than 1, let's look at these two limits. So assuming that a is a number that's larger than 1, what's going to happen to this logarithm as x gets larger and larger and larger? Yeah, I got to vote for goes to infinity. We need to unpack what logarithm, like kind of what this means. If I say log base a of x, yeah. So yeah, I'll just write down this inverse relationship there that I had last time. So if I have log base a of x equals y, that has all the same information as this statement, a to the y equals x. So I'm just stating the same idea using an inverse function. So if we're okay with that, do we buy that this limit is infinity? A is not changing. So it's only x that's varying. So basically, we're looking at these two statements up here, we're looking at what happens to y as x gets very big. Yeah, hopefully we can see that those things they're not gonna grow like at the same rate, but they are both going to be increasing without bound. What about the limit as x approaches 0 from the right? I'm going to vote for negative infinity now. So again, let's look at this a to the so we have a to the y equals x. If x is, let's start with this first of all. Is it possible for x to be 0 in this situation? There's no positive number, let alone no number bigger than 1 that I can raise to a power and get 0 back. So we know that I can look at the limit as x approaches 0. I can't look at what happens when x equals 0. Are we okay with that fact that this limit is negative infinity? Yeah, I mean, I'll just show you a couple ways here. So, let's look at our kind of the first way we looked at these things. Let's look at 1.1, 0.01, 0.0001, and so on. And let's just to make this even more simple, let's say log base 10 of x. What's log base 10 of 1? It's not 1. Again, think about what logarithms mean. 0, right? If in that situation, doesn't matter what the base is. No, any real number raised to 0 is 1. What about 0.1? What's the log base 10 of 0.1? Negative 1. About 0.01? Negative 2. And negative 4. So if I keep picking smaller and smaller positive numbers, there is no limit there. That cleared up a little more? All right. Moving on. Let's find this limit here. the limit as x approaches 0 of this log base 10 tangent squared x. Actually, there's, never mind. We'll do it here. So how can we start thinking about this thing? Write this. So I can also re-express this as the limit as x approaches 0, log base 10 of tangent x squared. Sure. Any questions about why that's legal? All right. So we've got a couple of rewrites here. Where can we go from here? Go ahead. What is the limit as tangent x approaches 0? Okay. I think that's true. So then, applying the limit law there. So here's something I know. The limit as x approaches 0 of tangent x equals 0. So from here, knowing that as x gets closer and closer to 0, that inner function, that tangent x, is going to get closer and closer to 0. So then what does that mean the overall limit is going to do? It's going to go to negative infinity. So once we break that down a little more, we can see something that hopefully is a little easier to reason through. Any questions here? There are a lot of ways to look at this, and I did not foresee this way here, which is fine. Yeah, that's basically what this is. Yeah, so if I wanted to write this as, taking the limit out of it for now, 2 log base 10 of tangent x is equal to y. Basically what that y says is, what power do I have to raise 10 to get y? And you what? So let me answer what I think you're getting at. I have to evaluate a limit because I can't simply, log base 10 of tangent of 0 squared does not exist. So I have to look, if I want to look, I have to look. Since tangent 0, I can't take a log. But so we actually can look at it from both sides. Thinking about that original form there. Any other questions? So you've probably seen this before, but so this is just an application of the definition of a logarithm. to get a special case out of it. If you see this notation, which I'm guessing a lot of you have, ln of x, natural log of x, that is a specific logarithm of x, or logarithm where the basis. So if you do natural log of x, y, that gives you the same information as e to the y equals x. The natural log of e to the power of x. I'm going to vote for x. I agree. So just to kind of unpack it a little more, if I say natural log of e to the x equals y, that means y equals x times the natural log of e. What's the natural log of e? It cancels, I mean, it's 1, yeah. Same sort of situation going on here. E raised to the natural log of x. This is one thing we're going to get in the habit of in a little bit. I mean, I think you have all these algebraic tools that you know how to do. I mean, you can multiply both sides by something. You can add the same number to both sides. You can take the derivative of both sides, things like that. One thing you're probably not used to, even if you've done it before, you're probably not used to doing it, is you can do what's called exponentiating both sides, which is really useful for solving equations. And one of the reasons I pushed the quiz out to Wednesday. And we did this, didn't we? Natural log of e equals 1. Just to make this even more clear, if I rewrite this as the log base e of e, what does that say? Like log base e of e, what am I really getting after there? Yeah, exactly. Which is hopefully makes it even more clear that that needs to be 1. All right. So given the natural log of x equals 5, I want to find the value of x. So if you know what logarithms say, you can pretty easily re-express this. There's this idea I talked about of exponentiation. This is absolutely something you're allowed to do. If I have the natural log of x equals 5, then I can use e to exponentiate both sides. And what I mean by that is raise e to the power of the left-hand side, raise e to the power of the right-hand side. Right-hand side becomes e to the 5th. What's the left-hand side equal? X. Is that something you've seen before, or is that something we're not super used to? Seen it before? Ever seen it? Yeah. I'd be willing to bet that most of you are in the, even if you've seen it, maybe you're not, it's not a habit. Any questions on how that works? All right, how about this one? I want to solve for x here. E to the 5 minus 3x equals 10. So, I mean, just like any other equation, we want to isolate x. So how can we start doing that? So yeah, just like exponentiating both sides, I can do this. Natural log of 10 doesn't really simplify any further. What is the natural log of e to the 5 minus 3x? 5 minus 3x. From here, hopefully it doesn't seem too scary anymore. I got negative 3x equals natural log of 10 minus 5. And x equals 5 minus natural log of 10 over 3. Any questions here? Go ahead, Thomas. I would hope. So I would prefer it, but like, if I asked for an exact answer for any reason, who's giving it? I think I did on the quiz that I just gave. If I didn't, then don't worry about it, but I think I meant to. Also, you probably already noticed this with web work, but if you start trying to round things, I mean, it doesn't tell you how accurate you need to be. So you're better off just leaving it in that exact form. Any other questions about this thing? All right. Yeah, I want to express this thing as a single logarithm. So based on the laws of logarithms we looked at, well, what's something we can do here is yep. So I mean, there's a clear relationship between, or not clear, I should say, but an explicit relationship between coefficients and powers. So natural log of a plus the natural log of b to the 1/2, which could also write like this: natural log of radical b. Almost there. Now what? Natural log of ab to the 1/2, or natural log of a radical b. Gordon?
So all your logarithms, like
The only reason it has this special notation is because the value of e is so fundamental to a lot of things in exponential growth and decay. So we just give it a special name, but no, it's a logarithm like any of the other ones. So it's every single property we've talked about, every single limit, every single property, like everything we've talked about applies to it just as well. Good question though. Absolutely. It's not going to be, so another thing you've probably seen is this, just have log of x. What's the implied base there? Okay. So for what we're going to be doing most of the time, it's not going to be nearly as important as natural log, but be ready for that notation as well. If the base is left off, we're implying the base 10, the decimal log. All right. So log like this, log base 8 of 5. There might be a couple of you with the calculator that can do this directly, but I'm guessing that's not true of most of you. But there are ways around that. So let's start off like this. And if anybody's seen this before, they might have seen it given to them as a formula. I try to get away from that, but it's a pretty easy process to build back up. So I'm trying to find this thing, right? I'm trying to find what log base 8 of 5 is. I'm just going to call that x. Can I re-express this as an exponent somehow? A to the x equals 5. So now I'm solving this equation. So now what I want to do, I want to solve for x. And the thing I want to solve for is contained on an exponent. So what do I need to do to have a chance of solving it? Maybe this is not obvious yet. So keep in mind this property of logarithms. Log base a of x to the r is equal to r times log base a of x. So if I want to be able to re-express these exponents, logarithms allow me to do that. So I'm going to take the natural log of both sides. Gives me natural log of 8 to the power of x equals natural log of 5. Now that I've done that, what can I do with that exponent? Bring it to the front. So now I have x natural log of 8 equals natural log of 5. And finally, I have x equals natural log of 5 over natural log of 8. Is that something you can take to a calculator? Has anyone ever seen that base change formula for logs before? Yeah. In my opinion, you need to rely on that formula so that you can put the numbers. You don't know like why you're doing all the transformations. I would recommend doing this because probably commit this process to memory. Question? Absolutely any log. So I mean, but the whole point for my whole objective here was to go to my calculator, right? So, and if you want to test it, most of you have calculators that can only deal on these two bases for logs. If you compute both of those, see if Apple can do either one of them. Careful. Log base 10.
Just to clarify.
Yeah. And really, there are a lot of situations where in certain things can be desirable for what you're doing.
Now, what's the difference between natural log and
It all depends on the question you're trying to ask. So let's just write down these two things: log base 10 of 100 and log base or natural log of 100. Are these going to be the same? No. So they're not going to be the same. So in this process, like the way we went through this, I used the natural log really because it was the one we were just talking about, and I kind of gave you the hint that that's going to be the one that we're going to be dealing with the most. But really, to do this calculation, all I needed to do, the only and the reason I use natural log, really, I didn't need to use natural log. Like you said, I could have used log base 10. I need something I can compute. But really, I bet if you went to Google and typed in log base 8 of 5, it'd probably give you. So yes, natural log of 5 is different from log base 10 of 5. But I only care about the ratio of those logs. The ratio, so yeah, I should be clear about this. Natural log of 5 is not equal to log of 5. Just like natural log of 8 is not equal to log base 8 or log of 8. But those ratios are guaranteed to be the same. But over here, I mean, these again, this log base 10 of 100. This one's 2. I would need a calculator to figure out what natural log of 100 is. Something 3 or more. Sounds good. So, and then this kind of reminds me. So if I write something like this, A over B equals 1 over 2. True or false, A equals 1. Heard a lot of sounds. Heard a true. Heard a false. Yeah, it's false. A could be 1, but like, couldn't I also say that A equals 6 and B equals 12? So, and I think that's a temptation that people fall into sometimes at every level of seeing a fraction like that or seeing a ratio. The ratio says nothing about what the two like related quantities are. Just tells you how they're related to each other. So I think this is what you so log base 8 of 5 over log base 8 of 8. Yep. So let's think about it this way. Log base 8 of 5, the numerator, that's hard to simplify. What's log base 8 of 8? 1. So that takes me back to what I originally gave you, log base 8 of 5. So yes, all of these things, all these links in this equality are equal. It's just the one on the far right is not practical. I can't do anything with it if I'm trying to approximate it. Good question though. All right, and I think that was it. Nope. I think it will be. We've done a graph of these things. All right, so that was the end of the marathon that is section 3.2. All right. So this section is now we're going to take those log and exponential functions and apply differentiation to them. All right, so I believe that I showed this to you in the past, where this constant E comes from. So I gave you both of these, maybe Friday, maybe Wednesday, but are we okay with the claim that both of those are essentially the same? So I mean, then really, so you'll see both of these as definitions for E. They essentially behave the same way, but it really depends on kind of where you see it given. I'm gonna go through this proof. I'll post it online though later. So I think I owe you proofs on a couple of things. So the inverse function theorem, I want to take another whack at, and then this, I'll give you the full proof of this, but I'll put those online later today. But section 3.2 kind of got away from me more than I wanted it to. Thomas? No. I mean, and they're really at this stage. The biggest thing they're useful for is just for seeing that these derivatives all come from the same place, and they're not arbitrary. They absolutely do have a reasoning behind them. So I'll come back to this. Let's look at these differentiation rules. So derivative of log base A of X. So again, this is any base. One assumption I should give you is this, is that A is positive and A is not equal to 1. So given that, so the derivative of the log base a of x is what it is, then what is the derivative of natural log of x? Will it be log with what base? So up here, I mean, regardless of the base you were given for the derivative of log base a of x, the derivative is 1 over x times the natural log of a, right? So this is going to be 1 over x times the natural log of e, which is 1 over x. So this is hopefully highlighting another reason why in calculus we really prefer the natural log to work with. Calculus is a lot simpler to deal with. Oh, I'm sorry, I thought there was something more in that slide. All right. Any questions on either one of these? Basically, one is just a more specific take on the other. All right, I want to differentiate this. So f of x equals log base 10 of 2 plus sine x. So I just gave you a new rule how to differentiate log functions. What other techniques we have to apply to this? So definitely logs are to perhaps chain rule. Do we agree that chain rule is going to be necessary here? I see some nods. Why is chain rule necessary here? Thomas? So 2 plus sine x, let's call that g. And then I'll say that h is, what's the outer function then? Log base 10 of x. That allows us to write f of x as h of g x. Any more questions? All right. So where do we go from here? How do I get this derivative? Sebastian? Okay, so let's get those things. What is g prime of x? Cosine of x. What is h prime of x? One over 10 natural log of x. I believe we got the pieces. Yeah, 1 over x times the natural log of 10. All right, I think we got all the building blocks that we need. So what's this derivative of the whole function then? Found those way too late. How we doing? Any questions here before I move on? Oh, went too far. All right, how about this one? Now I have a proper natural log. So I need a log rule. Do I need a chain rule again? Or Thomas, go ahead. What's that? Do you have to or do I have to? All right. Okay. So let's get a derivative for this one. How should I begin? Okay. So you want to do chain rule. So let's set this up. I'm going to say that f of x is equal to composed with h. So if I say that, what are some good candidates for g and h? G is x cubed plus 1. And h is, yeah, I think so. So yeah, be careful how you're composing. But yep, so g of x should then be, or h of x, I think, should be x cubed plus 1. In that case, what should g be? 1 over x? Now you're good. You're getting into the derivative. Yep. So now that we have those, we can find their derivatives. What's the derivative of natural log of x over x? And the derivative of h is 3x squared. So I believe we have everything we need now. So f prime of x is going to be equal to what? One over x cubed plus 1 times 3x squared. 3x squared over x cubed plus 1. How we doing? All right. A derivative of natural log of x. We need chain rule again? Okay. Sounds like yes. So if f of x is equal to natural log of sine of x, what are our inner and outer functions this time? All right. So we know the derivative of sine is sine of x is cosine of x. 1 over x. Okay. So then if I want to differentiate this entire function, what is this going to become? 1 over sine of x times cosine of x equals cosine of x over sine of x. Can I simplify that even more? That's cotangent of x. Simplified at the end. Okay. Right, natural log of x square root of that. First, let me ask this question. Is this true? No. I got some votes for no. Why not? There you go. So that's one thing I want us to be careful of is that. So this is not true. This would be. But that's not what we have. So now that we're on the same page there, how can we handle the derivative of the square root of natural log of x? Chain rule again. So often. So I want f of x to be g composed with h again. Talk about g and h. What's g going to be? This time the natural log is going to be the inner function. So g prime of x will be something, h prime of x. What is g prime? 1/2 x to the negative half. 1 over 2 radical x. And then h prime will be 1 over x. All right, so now I think we're ready to start our first pass. What's the derivative going to be? Sebastian, question? What? 1/2.
Yeah.
So what's raised to the power of negative 1/2? The x or the natural log? Yeah. And by natural log, I meant the whole thing. So 1 over 2 times the square root of natural log of x times 1 over x. Does that seem correct? Any questions on that example there? I don't know if this is a 3-minute example. I don't think that it is. So rather than rush it, leave part of it for next time, I think we'll break here. Any questions about anything from today? If you still need a quiz